Hi, I'm George Folku. I will speak about the future of computation using C++. I'm a computer scientist. I'm working in the computer science laboratory in Paris-Saclay in Orsay, France. And my main avenue of work is trying to make people compute complex math faster to solve bigger science problems. Let's speak about science problem in a bit. For a long time, people were actually doing experiments to perform their test on their hypothesis and try to derive scientific knowledge. But as soon as science were actually complex enough that actual experiments were complex, we were requiring to have an actual numerical way to simulate the real world and then draft theory. And the science of scientific numerical computing started to be a large amount of time spent by scientists. And those scientists are usually not computer science specialists. They want to do science and they started, at some point have issues. They had issues because for the longest time they could actually just wait for computers to be faster just by waiting. And at some point the computers were so complex, so heterogeneous, so full of cores and special computing units that they had to make a conscious effort about their code to get the performance they deserve. That's what Herb Sutter called the free lunch era. And the free lunch is over. You cannot just wait for your transistor to do your work. You have to actually write code that exploits them. But that's an issue because the scientist, he doesn't want to do numerical computation, he has to. So how can we make this work of writing numerical simulation something he can do properly without having to pull her hair or whatever? So, as I say, for a long time, CPUs were simple. They get more complex by the era of the multicores and the CMD extension set, but it was also still manageable. But now, with all the different kind of GPU, accelerator, distributed computers, it's very hard to actually manage to write a code that makes sense for a scientist and which is performant enough so results can be extracted from this code. So, what should we be doing? Well, in our stance, what we want to be able to do is find a way that, without being disruptive and while being able to take advantage of domain-driven optimization opportunities, still try to find a way to provide an intuitive API for users while supporting in an efficient way the wide architectural landscape that actually is the norm in HPC. So what should we do? Which language should we consider to do this? Well, depending on the point you are looking at, you have a bunch of options. Either the good old Fortran or the more dynamic Python or R, which is a crowd favorite right now. But one thing is sure is that C++ is basically the one thing that you can actually fit into all of this. You can build complex API with intuitive design. You are sure to be efficient because you are close to the metal and most of the parallel systems as a C or C++ interface. So what does it mean for us? Well, C++ for now a decade had a surge of interest. It started basically a new life after its C++2 and 2011 norms that pushed C++ back on the front of the international language scene. It also created momentum with this train model of release that every 3 years you get a new standard with either bug fix or new components to play with. C++ 14 was a hit, and so was C++ 17, and we are entering into the era of C++ 20, while the committee is actually drafting C++ 2023. A lot of the past has been fixed, either in terms of specification or ugly syntax. And new tools emerge and new idioms also emerge from both academia and industrial use. So it's a very nice place to be right now, writing code in C++, because you have a huge amount of tools you can now play with, and you can actually push those into corners that we will be exploring soon. And C++ has another advantage. It's what we call a structuring language. It's something you build infrastructure with. You build the code that make other code runs, either being operating systems, computing systems, and so on. C++ is a language that shines when it builds libraries and other tools. So what about solving our expression problem using C++ as a way to design libraries that act as languages. And that's what we will try to speak about in this talk. We will be touching different subjects, and the first one I want to speak about is one fundamental change of paradigm in the way you can design C++ libraries. This paradigm is basically looking at code or code fragments as a valid data. And for those who know me from other video or other talks about the subject, you know perfectly where we are going to be going. We are going to speak about metaprogramming. And C++ metaprogramming as more detailed way. For a long time, C++ metaprogramming was in disarray. You were either using C++ preprocessors, using Boost preprocessors or the Chaos library, and you were relying on macros to lay out codes fragment around your program. Or you could use code generator written in another language, which was a very classic way of doing things in some business, using things like UML to code converters and so on. Or you have to deal into the actual dreaded metaprogramming that was abusing template functions and template classes. You were embedding types and code fragment into reusable types that you will nest one into the others. You will probably do unspeakable things to get your code to write, and then to compile, and then to work properly. Don't get me started on how you should be debugging this. It was a mess. It took a long time to compile, and everybody was not very happy about this. So why should we care about C++ programming if it's that bad? Well, it was that bad. But the cool thing is that a lot of things actually changed. First thing is that prior to C++ 14, 17, template metaprogramming was focusing on type, was playing around C++ syntax to convey meanings that the original code didn't have, like using recursive structures to express iteration, or use partial specialization to express conditionals. There was few abstraction, and they were all low level. The paragon of this era is Boost MPL, which provided sort of iterators and algorithm on top of types or type list. It was working. It was quite a nice feat of engineering, but it was cumbersome. You had a code which was very different at runtime. That was the code we were using to write template metaprogram. It was like two languages mashed together. Well, what to do then? Something changed in C++ 11 and 14 and afterwards is that some of those template metaprogramming idioms were actually inserted into the standard. And instead of focusing about the syntax and where your type should go and how much recursion you should be doing, you could start actually focus on the fact that metaprogramming is manipulating code fragment. And metaprogramming is not a sorcerer's activity. It's a variant of automation applied to the code writing process. Metaprogramming is writing code that automate code writing. And as soon as you can wrap your issues, your problem, as an automation problem, metaprogramming can actually be used as a solution. So the problem was, what is this notion of code fragment? What does it mean in C++? We never had that. So we make a short detour looking at other languages. Some of you may not be familiar with it. I will try to be very gentle into their introductions. But let's look at one of those funny language that has this kind of metaprogramming systems. Let's have a look at Objective-CamL. Objective-CamL is a French design functional programming language, so in which everything is a function, everything is a value, you have no states, everything is pure, okay, to some extent. And some variant of Objective-CamL has a way to actually express the notion of code fragment. The variant I will talk about is now more or less deprecated and has been replaced by some other tools from the OCAML ecosystem, but it was interesting to speak about MetaOCaml. MetaOCaml was about to express the notion of code fragment as an object with a type. And we will see that having a type in the Objective-Caml is very important, because Objective-Caml has a type checker that will check that your code makes sense. And encoding information into Objective-Caml types was the main activity you want to have with it. And as soon as you have a box that can contain code and that you can treat it as an object, a lot of things goes easier and faster. So let's have a look. Three main tools were provided by MetaOCaml: a way to create a code fragment with a construct called brackets, a way to inject code from one fragment to another, which was the escape sequence, and executing a code fragment at runtime. So the metaprogramming of Caml was written at compile time, statically, and was executed as a program run. It's not compile time metaprogramming. You should have a look at Haskell for that. But it's very interesting nonetheless. Let's have a look at a simple example. So this is the thing you could actually write using MetaOCaml. You can actually make a variable A, which is a code fragment. We have this small brackety-like notation there. And A is a code fragment that say I will evaluate to 1 plus 2. The code 1 plus 2. So the type of A is given by the type checker on line number 2. A is a code that returns an int when evaluated, and that contains whatever the code contains. We can build another code fragment B there, which is, we see it's a code fragment because we again have the bracket syntax. And what happens there is that we want to do 3 times whatever the code that was in A. It's not 3 times A, it's 3 times expand the code from A, which also turned to be 3 times the code that contain 3 times 1 plus 2, which is a code fragment as said by the code type there, and these things will evaluate to an int. And then we can have, I would say now I want to execute the code, and C is the result of the execution of the code stored in B, and it's an int as per the specification, and 3 times 1 plus 2 is actually 3 times 3, so it's 9 again. So there is a very thin syntax around code blocks. It's basically code with those small brackets. It's very lightweight. Code fragment as a type, that's very interesting because so you can actually reason about what's going on in the type. And everything is data. There is nothing special. You can write whatever code you want. It's a code fragment. So how does this help us with C++? Because that's where we want to be going, right? Well, how can we translate this in C++? So a code fragment is a piece of code that you can write, contains arbitrary expressions, but it's not executed right away. It's executed a bit later. Well, that's exactly what anonymous or lambda function in C++ does. You can wrap a piece of code into a lambda and store it into an object. And your lambda object are basically code fragment. They have a type, you don't know it, but they have a type, and you know that when you call the function represented by the lambda function, you will get some output. It's a code fragment. The injection things is basically just calling function from another function and relying on the inlining of said function. You can replicate code by using valid templates to just repeat over and over and over again a fragment. And the execution is whenever the compiler starts to compile these things. That's your metaprogram execution. And the cool thing is that a lot of things that were very complex back in the day, like compile time conditionals, compile time application, get support from the language. If constexpr allows us to do selection between code fragments, we can have a very thorough typing and support for constraints using concepts and requires clause. We can compute arbitrary code as constexpr function, and the cool thing is that lambda functions in C++ 17 are by default constexpr. So lambda themselves can be used as a context per context. And the one other thing is that the notion of non-type template parameters, NTTP, has been extended in C++20. And one thing we can right now do is take a lambda or an arbitrary context per friendly structures and use it as an NTTP, which are not now restricted to integers or booleans or things like this. Well, let's have a look at what's going on. What can we do with all of these things? So we have selection, we have replication, we know that we can pass all of this in different contexts. We could actually write generic function composition because it's just a function taking two code fragments and generating a new code fragment that just calls the first and then the second. We can unroll code using variables. And for a very, very efficient way of, for example, iterating over tuple members, we can filter tuples, we can apply function on tuples. That was basically the goal of Boost ANA library by Wisdom. And a very interesting thing that is possible now is that you can actually pass compile time string to do whatever. This is what the CRTE, the context per regular expression library by Hannah Dusikova does. You just write a context per string and you get regex out of it. So that's a lot of things that we can do with this new style of metaprogramming. And let's have a small example so we can actually see what we are speaking about. So there is multiple things going on. So what we want to be able to do is what happens starting in 14. We want to have some kind of automatically unrolled context per 4 that takes an arbitrary piece of code and replicate it for every value in a context per range. So we have this funny syntax that say context per 4 over the range -5 + 5 applied to a lambda function there that takes an index, and we just print the index there, nothing very fancy. Well, there's a lot of things going on there. The first thing is that it looks like we call a function inside our context per 4 template specification, and we have this auto index lambda things. So first thing first, what is range? So range is a basic structure. It has nothing special, no private members, no virtual function, no inheritance with those properties, just a bunch of integers. And those functions are called structural types, and you can just use them directly inside non-template type parameters. So there what we do is we build an instance, a context per instance of range that contains those values, -5 + 5, and just compute whatever is to be computed. And we pass them as a template parameters that we check their line 6 by these auto range things. So these things say that I will get a range, I don't know which type is it. And I will get something of type code, which is the lambda function there. Okay. And what we do is we do this other thing with yet another lambda function. Okay, so I guess you like them. So what we do, we build a lambda function that we capture by reference the code C there. It's a template lambda function that's a C++20 changes. So we have a parameters there, which is an integer sequence of type int with a variadic parameters n, which enumerate a given number, set number of integers. And what we do is we use this variadic nature of n to use C++17 for expression there to just keep calling C over each and every value of n starting from the base of the range. So if the range starts at -5, what we want to do is -5, -4, -3, and so on. And to do so, we directly call the function, the lambda function directly. It's an immediate evaluated lambda expression with an integral sequence that just will enumerate 0, 1, 2, 3, 4 up to the number of elements. And so this code is actually unrolling C for every different integral constant. We don't do something very interesting there with index because we just keep it this way and we print it. But the fact that we keep it in an auto parameter there is actually interesting because we know that at each call of this lambda function, we could have a way to know which index exactly it is, because the index is available at context per context because index is an integral constant. So that's just a code that unrolls a piece of code. But the interesting part is that this code actually looks like a code. I mean, it's a function that does something with its parameters, calling other functions. That happens to be lambda functions. There is no recursion over template types, there is no complex structures. But still, what we say is that context per for is a meta program. It automates some kind of code writing. Okay, so we can enroll code, we can do whatever, fine. But maybe we can do something more interesting. Yes, let's have a look at what we can do using this kind of metaprogramming. This is a result we obtained in one of our continuity library, which basically enroll by hand small matrices to perform matrix by vector multiplication. And matrix vector multiplication is something that you need to be very careful of the way you optimize it if you want to get performances. In this case, we compare to OpenBLAS and our handwritten C++14 template metaprogrammed GMV on the Arch 64 ARM processor. And what we saw is that up to 520 by 520, we were outperforming, or at least being comparable to OpenBLAS, which is one of the most iconic version of this function. And then we start to degrade because the amount of enrolling start to be counterproductive. But that means that we are able to write a regular C++ code using template metaprogramming that is able to be as good as what an assembly and optimized function is. We can go up to there. And this example is very important because it shows that even on those very sensitive fine-grained function, all the abstraction we use for the template metaprogramming just dissolves, and what left is the perfect code we want to have. So that's a very interesting experiment we did. We also do something similar using GPU with similar results. GPU is another issue because it's more like how to be able to handle all the transfer of memory, but it's a very similar system. Okay, so we have this template metaprogramming system, that basically act as an automation system. But now we want to go further than that. We want to design a library that looks like a language. And there is multiple ways to do this. Let's start with the most common one, which is defining embedded domain-specific language. So let's start about domain-specific languages first. A domain-specific language is a non-Turing complete declarative language that is designed to solve a kind of problem, and a single kind, by writing what you want to do instead of how you should be doing it. You probably use some of them. Make is a DSL, Matlab is a DSL, SQL is a DSL. And by 2004, David Abrams coined the term EDSL, like embedded domain-specific language, which is basically a library which is designed as a language inside a host general-purpose language. And one way to do this is to use metaprogramming and a very specific idioms to do this, which is the expression templates, the idioms, which is probably something you know already about. Expression templates rely on an extensive, and some people may say abusive, use of operator overloading and function overloading. And instead of having every operators or function calling some code on some types, do a computation, we build a type. We build a type that represents the operation, and this types remembers which value it should be using on it. And so we end up with this massive tree of expression, an abstract syntax tree, that we retrieve there, like this flattened tree things. And this type can be manipulated, it can be transformed, whatever you want, and you can generate the code you want. For example, there I'm just turning everything there into element-wise computation with a Pragma OpenMP on top of it. So you wrote that. Let's zoom a bit on that. We wrote this, sorry. The compilers generate this in this form, and we turn it back into this code. So there we decided to do OpenMP, but we could have done anything else. So you can have an arbitrary high API. This is a matrix API, it could have been whatever. And you know that you can actually generate the exact code you want. And that's very interesting. But there is some shortcomings on that. The most famous one, and we spoke about that at CPPCon 2019, last year, is that the main issue is that the terminals of the DSL IST, so the nodes that contain the value, are both storage, it stores data, which can be dynamically allocated, if it's a matrix, for example, and it's also something that spawns multiple trees. And it's very complicated in this case to do some sub-expression matching or build sub-expression from another one, because you will always have the risk of having a dendling reference to some portion of the IST that just doesn't exist anymore, which you should solve by trying to guess when you should just copy an IST like it is, or you should do a deep copy by copying every of its subtrees. The traversal of those ISTs is then more complex than it should be, and compile time are affected. And the better approach we wanted to have was to say, okay, just don't store any data in the DSL. Just write a symbolic, metaprogrammable expression that represents the computation you want to do, and do it later. So you can transform the expression, you can reason about the expression, you can compute things about it, and when it's computed, well, just call it. Let's have a look at what kind of a DSL we can bind this way. So this is a basic formula thing. We have some predefined variables there, x, y, z, and so f is a formula that computes this for some x, y, z, but I don't know what x, y, z is. It can be an int, it can be a float, it can be an array, I don't know. I know that at some point I need to know what does it means to do a multiplication with x and y, for example. Cool thing is that we could actually build variable on the fly by giving them name, okay, in this $parents thing. So this is g, which is the same expression, so we know that it's a product of mass divided by a distance squared. So we are apparently doing physics. You can do variable renaming, because renaming a variable is just evaluating the expression by telling that x is equal to mass, and every name is changed this way. You can do partial evaluation, because we can just say we evaluate some formula for only a given subset of its variable. You can mix formula together, and you can ask for full evaluation. And this code basically generates the least amount of code possible. And by the fact that nothing is actually stored inside the DSL tree, the tree is just a husk. It's just a context per representation of the tree. Everything there is context per until the point you ask for an evaluation. Which means that we can apply arbitrary transformation on the tree anywhere there, and then apply it to some values. And this kind of framing make designing DSL far more easier. Because there I'm just dealing with mathematical formula. I could derive, object building systems. I can probably write, state machine DSL or whatever. Just build the things and call it afterwards, and that solves so many problems. But the next step, and that's currently what we are exploring right now, based on the wonderful idea by Anna Dudsikova in CRTE, is use literal string as a DSL API. By doing so, we can describe and use an arbitrary syntax for your embedded language. You are not limited to whatever C++ wants you to do. And what we do there is that we basically write the apex of the automation system. We are building a compiler for an arbitrary language inside the C++ compilers. That's probably where I should have put some kind of yo dog meme, but well. It's very interesting because it means that you don't care about the syntax. You do whatever you want, and you just have to write your parser and your compiler as meta functions to handle this. And this is very interesting because there, for example, this is a very, very early part, is that you can actually write something that, I don't know, parse LaTeX and build the formula we just saw above. We can use concept to syntactically check and restrain whatever goes in. But basically, we can write whatever we want. Small tip of the hat to the extended user-defined literal suffix there that help us having this, but we could actually put that into a function or a simple type. But that's very interesting because this opens the way to have a very, very flexible DSLs. And I always think that this is probably what most physicists want to write. Just write the LaTeX things, put it into your code, and you're done. So let's conclude about this. So we saw that writing code is boring, especially when it's complicated because the hardware is complicated or the software specification is complicated. You can't really write everything by hand to handle this multiple amount of architectures, parallel architectures, or accelerators, or whatnot, or variant of the algorithm. So the alternative we want to push forward with new style metaprogramming is that you want to write automation. You want to automate the code writing. You just want to spend time writing the actual element of the code, which are non-trivial, and where human input is required. I will advise you to explore what C++ 17 and forward template metaprogramming provide. It's very flexible. People find new things every day. The type-based DSL is a valuable backbone that still needs to be done because it grounds the things into something that we know how to handle. And on top of that, we can build those string-based DSLs. And there is a new thing that we are really impatient to test. C++ 2003 or 2006 is supposed to have support for static introspection of types and code fragment, which means that most of these tricks and jugglery we do with templates, function, and context for lambda could actually be again synthesized in a more direct syntax. So that's something to explore. Meanwhile, thanks for your attention. I hope you learned something from this talk, and I'm available for questions. Thank you very much.